So we will conclude our discussion of non-parametric models by going over support vector machines. So as I was saying, support vector machines were very popular before, they've been essentially taken over by deep learning, neural networks, and random forests. So support vector machines were popular for three main reasons, essentially, or three main properties. The first one is that support vector machine construct what's called the maximum margin separator, which is a decision boundary with the largest possible distance to example points. So this helps a lot with generalization. Okay, so it doesn't try to fit the data points as much as other approaches. Second, support vector machines create a linear separating hyperplane. So the idea is, let's say we're looking at a bunch of data points and it's clear that we can't separate them linearly. So support vector machine, what it does is it maps the data into a new space where the data becomes linearly separable. And then we classify them in that new space before bringing back a decision to our original space. Okay, so that's why they're able to create a linear separating hyperplane, even though the data itself might not be linearly separable. Okay. So essentially they have the ability to embed the data or to map the data into a higher dimensional space using what's called as the kernel trick. So the kernel trick is consists in finding a kernel or a mapping function to take the data from its original feature space into a higher dimensional feature space that does not mean anything in reality, right? It's just a mathematical feature space, but it has this beautiful feature of allowing us to linearly separate the data in that space using a linear separating hyperplane. So the result is that data that are not linearly separable in the original input space are usually separable in the higher dimensional space. And the third property of SVMs is that SVMs are non-parametric. So the separating hyperplane is defined by a set of example points, not by a collection of parameter values. So unlike regression, we don't have to specify the number of parameters we're going to use in our hypotheses. So while nearest neighbors models need to retain all the examples, an SVM model keeps only the examples that are closest to the separating plane. And the reason for that is if you think about it, these are the most interesting data points for us as we try to build the classifier to separate multiple classes, right? We only really need to worry about points that are near the edges of each class rather than points that are deep into their class and that any classifier can easily identify as belonging to that specific class. So that reduces a lot the number of data points we have to worry about compared to k nearest neighbor, for example. So SVMs then combine the advantages of non-parametric and parametric models in that they have the flexibility to represent complex functions, but they are resistant to overfitting. So let's look at this figure, for example. This is a binary classification. So we have two classes with three candidate decision boundaries. Each one of them is a linear separator, right? So we're trying to introduce the idea now. Now each of them is consistent with all the examples. So as you can see, from the point of view of classifications, they're all equally accurate, right? They all achieve essentially 100% precision here. Now, logistic regression would find some separating line. The exact location of the line depends on all the example points. Now, the key insight of support vector machine is that some examples, like I said, are more important than others. And then focusing on these examples will help us generate a model that generalizes better. Okay? So, if you consider the lowest of the three separating lines in figure A here, you can see that it comes very close to 5 of the dark examples, 1, 2, 3, 4, 5. Okay, so although it classifies all the examples correctly, which means it minimizes the loss, it's still probably not a very reliable boundary, right? Because it is just too close to these boundary edge points right there. I mean, I could easily see a mistake happening if we go with that classification boundary. Now, SVM addresses this issue. Instead of minimizing expected empirical loss on the training data, SVM tries to minimize expected generalization loss, which is in reality what we care about, because we're in the business of making predictions, and what we care about is how accurate our predictions are. We don't really care about how accurate we are in predicting what already happened, because that's the past. What we care about is our generalization loss. So, even though we don't know yet where the new points will come in, but under the probabilistic assumption that they are drawn from the same distribution as the data we are training with, then we can probably minimize generalization loss by losing the separator that is the furthest away from the examples we have seen so far. So we call this separator, this dotted line right here, the maximum margin separator. And you can see that the margin in that case is how far each data point from each class is from that separator. So this is one out of all these models right here. This one is actually doing the best job in being away from the frontier points of each class, which means that that separator will have a much lower probability of generalizing poorly for a new unseen example. So the margin is the width of the area bounded by the dashed line. So this right here, this area is what we call the margin. Okay, and the question now becomes, how do we find this maximum margin separator? So let's go back then and just remember that when we're working with support vector machines, the classes are labeled +1 and -1. So we don't use +1 and 0 as we've done in the past. We use +1 and -1. Okay. And if you remember with regression, our weight vector W, we added a dummy vector, a dummy component to represent the intercept. We're not going to do that here either. Okay, so that's another difference as far as logistic regression. Now, with that in mind, the separator then is defined as a set of points x such that w dot x plus intercept vector b equal 0. So we could search the space for w and intercept b with gradient descent to find w, not to minimize the classification loss like we did with regression, but to maximize the margin. Okay, with the constraint that all the examples must be classified correctly. Okay. However, it turns out there's another approach to solve this problem. Okay, essentially we use an alternative representation called the dual representation, which is the optimal solution is found by solving this equation. So find the maximum by changing alpha such that the sum of alpha, so alphas corresponds to the number of dimensions of the feature vector, and minus half this summation right there. The only constraint we have over this equation is that all the alphas have to be positive, and the summation of all the alpha j times yj must be 0. So this problem is called the quadratic programming optimization problem, and we don't have to worry about it. There are already software packages that run this optimization for us. Once we've found the vector alpha, we can go back then and get w, the vector w, using the equation w equal summation alpha I yi xi. Now, there are three important properties of this optimization problem. First, it's this expression is convex. And you remember from our previous discussion, convex problems are fantastic because they guarantee us the presence of a global optimum, right? We don't have to worry about being stuck in a local optimum somewhere. So that means we can easily find a single global maximum. Second, the data enters the expression only in the form of dot products of pairs of points, right? Which is, you can see here, xj dot xk. Okay, so this second property is also true of the separator itself. Okay, once we found the optimal alpha j. The final important property is that the weights alpha j associated with each data point are 0 except for the support vectors, the points that are closest to separator. Okay, and because there are usually very few boundary points, okay, or support vectors like we call them here, so SVM is much faster to run than other non-parametric methods like nearest neighbor, for example. Okay, or even parametric methods like linear regression. Now, what happens if the examples are not linearly separable? So that's where the kernel trick comes in. Okay, so we design a kernel such that we're able to map the entire problem into a new space where this optimal linear separation can be found. Okay, and once we found that optimal separator, then we can map it back to the original input space. Of course, when you map it back to the original space, it's not going to be linear anymore. It's going to be some wiggly nonlinear decision boundary between positive and negative, but we know that it's going to generalize much better than trying to fit directly a decision boundary in the original space. Now, the kernel method can be applied with any other algorithm. It doesn't have to be support vector machine, as long as you can reformulate that algorithm as using dot products of data points like you see here. If that's the case, so you can easily say, okay, why don't I apply a kernel to logistic regression and map everything to a new space where the regression is easier to do? Well, that's fine if you can express linear regression in an equation where you have the dot product of pairs of data points, as you can see in this equation. Okay, so that concludes what we need to to review for non-parametric models, and I'll see you in the next lectures.